Okay, yesterday we started talking about the energy needed to roll things, and I promised I'd do my homework and have it kind of a sensible, even if it's still a little hard to understand right at first, discussion of how we can more easily show that and use it. So what we said was that if we have a circular path here, we're going from one point A to another point on the circle, point B, and this is something rotating or revolving around the center with a radius r. We said that if we were looking at the linear speed here, we call it a tangential speed right on the edge, we would define that as the distance traveled would be the radius times the change in the angle, delta theta, and then it would take a certain amount of time, delta t. Another way to look at this is that we don't really cover is something called angular velocity, and that's just when you've got something spinning, how fast is it spinning? That would include any point along this radius, and it's because it's going through an amount of the angle every second. And that's this lowercase w looking thing that's omega, and that is going to be the change in the angle divided by time. So we can see that these two are actually pretty closely related. If we combine these, and this will be important later, this v is really just r times the omega. We're going to use that in relationship later to bring it back into something that we understand a bit better. Okay. We also briefly mentioned something called a moment of inertia. A moment of inertia is a measure of how hard it is to get something to spin. It's like mass is in linear motion with inertia. So we have a kind of an angular or spinning inertia. Parentheses, like mass is for straight line linear motion. And what we saw was that this isn't just a measure of the mass. Certainly something that's really massive is going to be harder to get to spin. But what we saw yesterday with our little experiment is that it actually depends on the distribution of that mass too, because both the ring and the disk had the same total mass. But the disk was faster, indicating that it needs less energy to get moving. And the reason for that is if we've got a ring here, and let's call it a same size disk, they both revolve about the same center in our experiment. But this one's got a lot more mass towards the center because it's uniformly distributed. This one's all out at the ring. Well, think about this. We've all seen Olympic figure skaters who start out a spin and then bring their arms in and spin very, very quickly. Same sort of thing. If you've got more mass on the inside, it's easier to spin that, or easier to spin it quickly. Whereas if you put your arms out wide, you get much less of that. And as an experiment, we could actually do this if I have a volunteer. All right, Morgan. Are you get motion sick? Okay, good. What I'm going to have you do is hold on to a couple of weights here. You can come on up. The video right now is showing just a blankly staring audience, so I'm going to move that over quick too. We'll be in the darkness, but... Oh, there he is. Say hello, Morgan.
Hello.
Hello, Morgan. Yeah. This stool spins. So I'm going to have my lovely assistant have a seat on this. Try and keep your feet up. I don't know that you're like, yeah, if you can put it up there, great. And put your arms out. Okay, I'm going to get him spinning, and then after I'm spinning, I want, no, straight out, come on now. After you're spinning, I want you to draw them in. Are you all right? Okay. Careful now. Use your abs. Now, bring those in. Woo, and put them back out. And he slows. Bravo. Most people fall off. That's well done. Okay. Same sort of thing. Same amount of mass spinning, but when he brings them in close, he spins a lot more quickly because mass in towards the center takes a lot less energy to spin. There is a way to figure out how much this is, and it goes on the definition of this moment of inertia. If we want to do let's consider this not as a ring now, but just as a path of something like my weight on the end of a string. So just a point mass. And we're going to follow that around. It's got a mass m, and it's got a radius of revolution of r. I'm going to tell you this without proving it, but the moment of inertia is defined as the product of this mass and the square of the radius that it spins. And that's that measure of how hard it is to get it to spin. Now, most things like our disk or even the ring are not just a single point mass. They're actually a distribution of those point masses. So if we now consider this to be a full ring, instead of the whole mass being at that one location, we'd have just a tiny sliver of it, like a delta M. And each tiny sliver would have a mass of its own. And if it's uniform, it'd be the same all the way around. But we're just looking at a tiny, tiny, tiny piece. If we want to figure out the entire moment of inertia, we can't just automatically do this. Instead, we have to take into account all these little pieces of mass at all their individual radii and add them up. So we could do something like do a sum of all of these over I, however many there are, times the radius of each piece squared. And this would work for a disk too. If we just considered this to be a little square with a mass of delta M, then the radius would be changing. But if we took careful measurements and added all of them up, we could find the total. Calculus has a smoother way to do this. I won't say an easier way to do this. Does anyone know in calculus, if you want to add something up, do a sum? What it's called? I'm not sure you guys have gotten to anything like that yet. It's called an integral. If you're in calculus, you might have done derivatives so far. Integral is the opposite of derivative. So derivatives are finding the slope of a line. Integrals are finding the area under the line. They're adding stuff up. We won't do integrals. I just want to show you where it comes in. So we would actually do an integral, which is this cool German S thing, right? Leibniz was the German developing calculus at the same time as Isaac Newton, but doesn't get much of the credit. But we do use his way to write derivatives and integrals. So S for sum, and we take the r squared and have now in calculus, instead of a delta, use a d, which means an even smaller amount. This is measurable. This is so small it's not measurable. We just take slivers and slivers. But there's techniques that help you quickly do this as you get into, this would be a Calc 2 course in college, figuring out how to now integrate. Whichever way you do it, you'll eventually get up to this total moment of inertia. Now, we aren't going to do any of those. Instead, what we're going to do is use a list of them And you can find this, you don't have to do it right now, but you can find this on page 262 of the textbook. There's a nice table that shows you a picture of it, shows how it's rotating, and then tells you what the moment of inertia is. You won't need to memorize any of these, they're all on the test. But let's say that we've got a ring. The ring actually ends up looking just like our single point. Because if we added up all of these individual masses and multiplied them by the square of the radius, it would just add up to the total mass times the square of the radius. So that ends up looking like our basic definition, mr squared. If we have a sphere, solid sphere, and we do this calculation, now this is going from a very small radius all the way out. The I is equal to 2/5, right? 2/5 mr squared. If we have a disk, like the one that we rolled down against the hoop yesterday, we come up with an I equals 1/2 mr squared. See, we have a hollow sphere, so this would be like a ping pong ball, tennis ball, something like that. It's 2/3. Okay, and on it goes. And as you learn calculus, you can learn how to figure these out. But they're all pretty similar and pretty easy to use. I mean, they're all based on this mr squared, and then there's some factor out in front of it. Okay, so big similarity there. Our interest is to figure out how much energy does it take to get this spinning, and that, since these particles in it are all moving, that's some sort of kinetic energy. So we're going to come back to this in a sec, but let's think of our spinning ring again. We're going to say, okay, we've got a little bit of mass out here at some radius. Well, if we want to find the kinetic energy from that, what we'd have to do is say, okay, each one of these little pieces, I'll call them mi, rather than writing delta every single time. It would be 1/2 times the first little chunk of mass times the square of its velocity, plus 1/2 times the second little chunk of mass in there times its velocity squared, plus 1/2 times the third little chunk of mass times its velocity squared, and we keep adding them. So we would come up with another sum. And if we chose it so that all of these were the same, well, we'd have 1/2 times mi, because we're just summing over I, times vi squared. Okay. Now, if we use that relationship that we had up above, since these are rotating, we had another way to write the speed. I'll come back here in a sec. This v is equal to r times omega. That's what's telling us how quickly this is spinning. So I want to use that. Another way we could write this then is k equals 1/2 times all of those m's times r omega squared. I'm going to distribute that squared here. And this would be their individual radii, but the angular speed doesn't change. They're all spinning at the same rate. So we'd get an r squared here from that squared, and we'd have an omega squared. But we know what that is. That's that moment of inertia. So if we add up all of these things, this is the same, the 1/2 is the same for everything. The omega is the same for everything. Omega squared is the same. So we're just adding up the sum of all of these mr squareds. And we said, just a little bit higher, that's what this is. That's what the moment of inertia is. So we can define kinetic energy as 1/2. The sum of these is our moment of inertia times the omega squared. So if you ever want something spinning, that's how you do it. That's still not great for us because we aren't going to launch into the whole background information that would let us use this easily. So instead, what I want to note is that everything we're going to be dealing with, all of those values of I are some number, some constant number, times mr squared. We have a 1 here, 2/5, 1/2, 2/3. I'm just going to call it C for constant. So this I becomes a C times mr squared. Now it was useful before to put this V in terms of R times omega to show this. But really, that omega isn't what we've been using either. So instead, if V equals R times omega, I could also say that omega equals V over R. And put that in here. So that would be, and square it, V squared over R squared. That should be lowercase r. Well, now I have the radius squared and the radius squared. That will cancel. So I can rewrite my kinetic energy in a much friendlier form for us. 1/2, still have that constant that comes in front of the moment of inertia, but now the R squared, so it's just the mass times V squared. It looks very much like our normal kinetic energy of 1/2 mv squared, which we call the translation, because it's moving side to side. This, I'll put a little r there, is the one we can use. So whenever anything's spinning, rolling around its center, we can use this and relate the amount of energy back to how quickly is that thing moving. Yes, Carter.
So on like questions, are you going to give us a constant? Or?
Yes, you'll know the constants for any shape.
Okay.
Yep. Let's take a look at our problems from yesterday, though, and set those up. We had 2 objects, both at the top of a ramp. Does anyone, well, you've got it in your notes. How high was that ramp? How high? 2.1 centimeters. Is that all?
It was 9 centimeters.
The difference in height, sorry. What, yeah, so I'm going to list this as H1, V1. I'm not going to list an X because there's no springs in this. We had, yep?
10.4 centimeters.
You had 10.4? Can we confirm? We had 9.
9.75.
Let's call it 10. We'll call it 10.0 centimeters. We don't have to be exactly right. And then down here, when it got to the bottom, H2, that'd be 0. What was the initial velocity? 0. And we wanted to figure out how fast would this be going. So we're going to want to solve for this V2. And I'll pause the video so you don't have to watch all of this. Let's go through and see if we can figure this out now using our newly improved work equation, where we have a change in potential energy, mg h2 minus mg h1, a change in linear or translational kinetic energy, which is the same as we've seen before, m times v2 squared minus 1/2 m v1 squared, plus now our new terms of rotational energy, 1/2 c m v2 squared minus 1/2 c times m times v1 squared. The last thing we can actually make some notes. There's no friction when something's rolling, right? Or at least friction's not taking energy out of it because it's not slipping anymore. So that means there are no I can't think of that word right now.
Non-conservative.
Thank you. Non-conservative forces. So our left side is 0. We'll get that in editing. H2 is 0. We said V1 is 0, so that means this term is gone and this term is gone. It was not spinning at all. So we have 3 terms left. They'll add up to 0. We have a minus mgh1, that's our potential energy, plus 1/2 mv2 squared, plus 1/2 c times mv2 squared. One thing that can make it a lot simpler, does anyone remember the mass of the ring or the disc?
The ring was 0.654.
Did anyone measure the disc?
0.654.
Same thing, but you know what? I don't even care. Because there's an m in this term, and this term. If I divide everything by m, they just go away. Because 0 divided by m is 0. Minus gh1 plus 1/2 v2 squared plus 1/2 c times v2 squared. Mass actually doesn't enter into this. The distribution of that mass enters in right here, but the actual mass doesn't. So I'm going to gather my terms with V2 together. I'll have a V2 squared times whatever's left, so 1/2 from this one, plus 1/2 times my C. I still haven't made this specific to the ring or the disc. They look the same at this point. When I put numbers in, the C is the only thing that's going to be different. I'm going to solve for the V2, so I'll add the GH to H1 to both sides. And then I have to divide by this factor to get V2 alone. The 1/2 plus 1/2 C, and that's equal to V2 squared. And then take the square root of both of those sides. So now is the only point that I'm ready to evaluate this. This is where I can say, is it a ring or is it a disc? And let's see what happens to V2. So let's put in for the disc first, because you guys were always my favorite. Who had the disc? Oh, no, we're going to do the ring first. That's a burn right there. That's a big burn. It doesn't really matter which one we do. Okay, so let's put in our values. G, 9.8 meters per second squared, times our height difference, which we made simple to be 10 centimeters or 0.1 meters, over 1/2 plus 1/2 times the C. And now here's where it matters whether we're talking about the ring or the disc. If I went back up to that, the ring has no constant before it, so it's an implied 1. It's just I is equal to mr squared, so that constant is 1. So let's take this out. We've got, I bet I can do, well, not quite all of it in my head. 0.98 meters squared per second squared from the top. Down here, I can do this part, 1/2 plus 1/2 is 1. And if I take the square root of that, I'm going to be really, really close to 1.
0.99.
Yeah. And take the square root of this, meters squared per second squared, meters per second. So we would expect that ring to be going at about 1 meter per second at the end of the ramp, which is substantially less than the 1.4 meters per second you predicted. How come?
Did the constant and that is more numbers.
Where did that extra energy go?
It's going into the
Into the spinning. So it's going slower than it would have had it slid down without friction, because it's using some of that energy that it got from the potential energy to make it spin. Let's look at the disk now. I'll do that in blue. Same formula here. So we're still going to get, that. I'll write it out, but we're going to get that same thing there. But now we have 1/2 times 1/2 times plus 1/2 times C, and for a disk, that C is also 1/2. So this V2 becomes 0.98 meters squared per second squared on top. That's a quarter. 1/2 times 1/2 is a quarter, plus 1/2 is 3/4, 3/4. What do we get? 1.14, taking the square root of that, meters per second. Certainly faster than the ring, which we observed. The disk reached more quickly, but still less than the 1.4, 1.45 predicted, because that would have been something that all of its energy went into translation. So what we're seeing here is that we started out with a bunch of potential energy. Previous to this, we would say all of that went into a translational kinetic energy, just getting something to move. But now it's split between that and getting something to rotate. We're going to have work time, but are there questions? Okay, please feel free to ask on them. The final homework worksheet on twirling, rolling, and spinning is covering these sorts of calculations. Okay.